Hello everyone and welcome back to Educator.com. I'm Dan Fullerton and in this lesson we're going to talk about rotational kinematics. So to begin with, our objectives. Understand and apply relationships between translational and rotational kinematics. Write and apply relations among the angular acceleration, angular velocity, and angular displacement of an object rotating about a fixed axis with constant angular acceleration, and use the right-hand rule to determine the direction of the angular velocity vector. All right, so let's start by talking about radians and degrees. And yeah, I know a couple of these are going to be a bit of review, but as we get back into rotation in more depth, probably worth taking a minute or two to make sure we've got these fundamentals down. In degrees, once around a circle is 360 degrees, and once around a circle is 2 pi in radians. And a radian measures the distance around an arc equal to a length of the arc's radius. So, the distance around delta S is circumference, or 2 pi r, or if you're measuring diameter, it would just be, pi times d. Now let's do a couple conversions again very quickly. 90 degrees to radians. 90 degrees, if we want that in radians, well, 2 pi radians is equal to 360 degrees, so we would get pi over 2 radians. Or 6 radians to degrees. If we start off with 6 radians, 2 pi radians is 360 degrees. Those cancel out. 360 degrees times 6 over 2 pi is 344 degrees. So, we've got our conversions, angular versus linear displacement. Linear position displacement we've talked about as delta r or delta s. Angular position or displacement we give by delta theta. So as you go around the circle, you have increasing amounts of theta, where s, the linear distance, is r times theta, or delta s is r delta theta. If we talked about velocity in the same way, linear speed or velocity is given by the v vector. Angular speed or velocity is given by the squiggly w, the omega vector, where velocity is the derivative of position with respect to time. Angular velocity is the derivative of angular position or displacement with respect to time. And when we talk about these angular vectors, the direction is given by the right-hand rule, something that's very non-intuitive. So if we think about an object going around a path like this, the radius to the side, take your right hand, wrap the fingers of your right hand in the direction the object is moving around that circular path, and your thumb will give you the direction of the positive angular velocity vector. So the angular velocity vector does not point in the direction the object is actually moving. Okay, converting linear to angular velocity. Remember we had velocity is the rate of change of position or displacement with respect to time, but we know that s is our r times theta, the radius times theta. Therefore, we could write that this is equal to d over dt of the derivative of r theta. But r is a constant. Our radius isn't changing. So we could write this then as v equals r d theta dt, which is r omega. D theta dt is r omega. So v equals r omega. Or if we want omega, omega equals v over r.